Welcome to part 1, Nano Diffusion in Washcode. So now we will have a look at the washcode structure. How does it look like and how can we model this kind of structure? And then we can see how we can simulate diffusion inside this structure. So first off, I have some SEM images from a paper from 2011. Here you can see 4 different kinds of washcodes. Each one has a little bit different structure. This is depending on the components that you use for each washcode. So it can be some kind of spikes, but it can also have circular grains. But they all have in common that they are really small in pore sizes. So the maximum pore size is about 500 nanometers in each of these structures here. And all of them have roughly 50% porosity. Just keep that in mind. We want now to model this kind of structures for ourselves in Geodict. So please start up Geodict and then we can start. I will go here to Model, Grain Geo, Create Grains, and click on the Edit button. Since we want to model really small nano spaced structures, we first set our unit to nanometer. Now we can start changing our values here. I will generate a little bit larger structure now, 400 voxels in size. Our voxel length should be 5 nanometer. So our total dimensions are 2 microns each direction. I will set this overlap mode to enforce object overlap. This will lead to more overlapping objects and to more clustered structure that we have at the end. I will set object solid volume percentage to 50% because this is what we assume, that we have 50% porosity. Okay, now I go to the object options, and first I will remove the ellipsoid object. I will only use spherical objects. So 100% spherical objects, and I don't want to have them all the same size. I click on edit here, click on log normal. This means I will draw from this log normal distribution randomly. I will have to put in the values here. So please take 70 microns for mean value, standard deviation of 40 nanometers, sorry. Lower bound 30 nanometers and upper bound 150 nanometers. This will now give you also a preview plot. So as you can see, there's slightly more small particles, larger one. Okay, this is all done. You can now hit OK and then click generate. Yeah, and this will take a little bit. Now Geodict will create a structure, draw a sphere from this diameter log normal distribution and try to fit it into our structure. And if you want to have some more information what's happening, you can always right click here and say show debug output with some kind of info what is happening now, more info usually. But this should not take too long. So here it is. It's our structure. Okay. And to make it look like a little bit more like the SEM images we have seen before, I will go and change the view settings here. So first click here on this color and visibility settings. And I click on load preset and say first your values. Right, so now our structure is here in white or gray, background is black. If you now take the depth slider and 100, then you have some kind of depth darkening here. This yeah, it looks a little bit more like an SEM image that you have seen in the last slide. All right, but what we can see now here is that our structure is a little bit, let's say, perfectly spherical. So what we do next is we add a little bit of surface roughness. This is done in GrainGeo, roughen surface. Here again, click on the edit button, change settings. First thing again, go nanometer, then can enter our values here. So our new method we've now implemented is the stochastic roughness. This is what we use today. And this will create some random noise added to our structure. For the feature radius, I take 40 nanometers, and for the maximum distance, I take 30 nanometers. Our operation today is use add and subtract, which means that we add some voxels on top of our surfaces, but we can also subtract from the surfaces to make some smaller dents or holes into the structure that we also already have. So okay, click OK and click generate and see what happens here. So this will now create a random field, combine it with our structure. This should also not take too long and give us a nice distorted structure. Now adding the random field. All right, and there it is. Here you can see now that our ideal spherical particles are not visible anymore of this kind of structure that we want. All right, so this is the first half of the step, and now we have to simulate some fusion, and this can be done in Diffodict, Knudsen diffusion. So Diffodict, Knudsen diffusion here. And yeah, Knudsen diffusion is some special form of diffusion. So think about this as follows. We have some particles, some molecules that will move inside our pores, but there's the pores are so small that the molecules will hit wall and then reflect and then go to the next wall and then reflect and go to the next wall. And in between they will not see any other molecule. So no molecule intermolecular collisions will happen. This is what the Knudsen diffusion. So, and then want to simulate that, click on solver options. Here to the solver options tab, and we could set up everything. Because we want to have a faster solution for today's workshop, I will change from auto distance, fixed distance. It will be much faster, but not so accurate anymore. For the average travel distance, I will simply take the suggested value. And for the simulation stopping criterion, I will go tolerance, but improve the tolerance a little. 0.005 is all right. And keep in mind, this is really important. If you have a better tolerance here, you will need much more time for simulation. So yeah, you can surely try it out for yourself, but for this workshop, this is absolutely long enough. Okay, so then I click run and then it simulate the Knudsen diffusion. So more or less now, billions of particles will be simulated. How they move from wall to wall, and at the end, take the travel displacement of our molecules, or in basic principle, how far did they travel from their starting to their end point and how much time. So, and this is then what you see here. result file of the Knudsen diffusion simulation. And here you see we have tensor for the diffusivity. But these values here will not give you not give you a really good approximation of what you want to know, because what is missing is the user or the right terminal velocity. This is what we will do now. We will activate user-defined terminal velocity, and we'll type something in here that's a little bit more common. And this is, for example, 20 degrees Celsius, so room temperature and air molecules. So air molecules, it gets that from literature. 464 meters per second is a value that we'll find in literature. So, and this is now value that is better diffusivity of our particles in room temperature. This is what you would get now. Okay, so this is it for part 1. And yeah, keep in mind these values here, they will be used in the third step for the simulation of our molecule movement through our channels. All right, so then for part 1.